Hello, hello.
Hello.
Yeah. Uh, we'll continue with number theory problems. So the first problem is this. If you write n in its prime factorization, p1 power e1, p2 power e2, and so on, you have to find the sum of all the divisors of n.
Okay.
You can take examples of smaller numbers and see, for example, let's say n is equal to 24. This is 2 cube into 3 power 1.
Right.
And now if you think of all the factors and try to do the sum of all the factors, so you will get 1 and 2 3, 4, 6, 8, 12, and 24, right?
Yeah.
So the sum here is coming out to be 3, 3, 6, 4, 10, 16, 8, 24, 12, 36, and 24, 48. Now, this number can be written as 1 plus 2 plus 2 square plus 2 cube. This is what? 4 plus 8, 12 plus 2, 14 plus 1. Okay, maybe we have missed the sum. We have done a wrong sum because 3,
E
6, 4, 10, 16, 24. Oh, it's 60. The sum is 60,
E right, yeah.
and you can see that this is adding up to 15. And if you multiply it with 1 plus 3 power 1, this is adding to 4.
Right.
So basically, what we are saying is when you do number of factors, what we do is p plus 1, q plus 1, and all, right?
Yeah.
That means it is p plus 1 times q plus 1 because there are p plus 1 choices for powers of 2 and q plus 1 choices for powers of 3.
Right. Yeah.
Similarly, here what we are doing is all the powers of 2 that are possible we are writing, and then all the powers of 3 we are writing. Obviously, the multiplication of this will give you all the factors. For example, this times this will give you 3 power 1. Then you'll get a 2 into 1, and you'll get a 2 into 3 power 1, and you'll get a 2 square into 1 plus 2 square into 3 power 1 plus 2 cube into 1 plus 2 cube into 3 power 1.
Right.
Notice that these are the factors that you had here.
Yes.
So basically, what we are saying is that if you want to do the sum of all the possible factors, let's call it sigma n, you can do it by multiplying all the prime numbers raised to the power e1 till that, starting from 0. So
Yes.
1 plus p1 plus p1 square till p1 power e1 multiplied with now 1 plus p2 plus p2 square till p2 power e2, and keep writing these products like this. That will automatically give you all the factors can be constructed like that, right?
Yeah.
Do you understand how this sum will give you all the factors?
Yes.
So this expression will automatically give you the sum of all the factors of this. Just like
Right.
here we had just two prime numbers, but we were able to generate all the necessary factors by this type of a product.
Yes.
So you need to keep this in mind. The sum of all the divisors of n can be gotten from the prime factorization of the number.
Right.
Okay. Next thing is find the largest exponent of any prime n that divides a factorial, any prime p. So basically, what I want is an expression for EP of n factorial, where if I write it like this, E2 of n factorial means what is the highest power of 2 that divides n factorial, not 2 factorial. Highest power of 2 that divides n factorial. So the answer to this question would be E2 of n factorial.
Yeah.
Similarly, you
Okay.
can generate E3 of n factorial and E5 of n factorial. We want the general expression for EP of n factorial.
Okay. Would it be like you divide like n factorial by p to see how many like multiples of p are in n factorial, and then you would do the same thing for like p to the power 2 and like onward?
So that is the general idea. Like, for example, try to calculate E2 of, let's say, 6 factorial.
Uh-huh.
So try to find that out first, then we can
Okay.
try to generalize it.
Okay. 呃 It's 4, E2 of 6.
How can it be 4?
Because it's 6 times 5 times 4 times 3 times 2 times 1. So you get 1, 2, and then you get 2 2's from the 4, and then you get 1, 2 from the 6. Oh, sorry, divides the factorial. Okay, so then, yeah, 720, and then the highest would be, one sec.
You do 720 by 2, what are you getting?
360.
Right.
And then you just keep on going down.
No, actually, that doesn't make sense. We should not do 720 by 2. We should do 6 factorial by 2. So 6 factorial is equal to 720. We should do 6 by 2. You get a 3 from here.
Yeah.
If you do 6 by 4 and you take the floor function, you get a 1. Here
Right.
also you should do a floor function. So you get 3 from here, 4 from here. There is no
Yeah.
way to do 6 by 2 cube. Floor function is 0.
Right.
So the power is 4. This was
Yeah.
obvious even by looking at the numbers,
Right.
because there is 1 power here, 2 powers here, and then 1 power here.
Yeah.
But right now the numbers were small. It would have been difficult if the number was a very big number, right?
Right.
But we are getting it by doing 6 by 2 and then 6 by 2 square and then 6 by 2 cube and so on, right?
Yeah.
It automatically became 0 when it was too big, right?
Yeah.
So when it is small, those ones you have to add, right?
Right.
For example, suppose you have to find the highest power of 5 that divides 156 factorial. So what I need to find out is E of 5, 156 factorial. So we'll follow the same method. We'll say, okay, 156 by 5 and take the floor function. Then 156 by 5 square. And then 156 by 5 cube, right?
Yeah.
5 power 4 is bigger than 156, so nothing will happen after that. Correct?
Correct.
So here you will get 31. Here you will get 6. And here you will get 1, right?
Right.
And you're getting 38 total, right?
Yes.
So what this tells us is that 5 power 38 can divide 156 factorial.
Right.
Why do we know that? Because when we do this, what we are saying is there are 31 numbers which are divisible by 5, 31 multiples of 5 coming up to 156, right?
Right.
But there are some of them which are divisible by 25. So extra numbers, extra powers will come from there, right? One extra power.
Yeah.
And some of them which are divisible by 125. So one more extra power,
Right.
right? Only one of them is divisible by 125, which is 125. And there are several multiples of 25 there,
Right.
right?
Yes.
So all of them will give one extra power, and this one will give 2 extra powers basically.
Yeah.
And these ones, the normal multiples of 5 will just give one powers. Correct?
Correct.
So in general, the expression for EP of n can be now written, because we have taken some small cases, we have understood the pattern. So we can now say that EP of n will be n factorial will be n factorial divided by p, take the floor function, plus, not n factorial. We have to do n divided by p. And then n divided by p square and n divided by p cube, so on till infinity. Obviously, when the powers keep increasing, eventually p power k would become bigger than n, it would become 0.
Yeah.
So this sum will automatically terminate, it will not go on forever, right?
Yes.
So this can be written as EP n factorial is equal to summation summation I goes from 1 to infinity, fact, floor function of n divided by p power I, right?
Yes.
And that automatically gives you the highest power of n, highest power of p that will divide n factorial.
Right.
Okay, similar question. Find the highest power of 14 that divides 180 factorial.
Okay. So wouldn't it just be floor function of 180 by 14?
What?
Wouldn't it just be the floor function of 180 by 14?
But it's not a prime number anymore, right? You have to be
Oh,
careful.
right. Okay. So you have to do the prime factorization of 14 and then do it for each one?
You have to think, okay, that prime factorization of 14 will be like 2 into 7, and
Yeah.
then think which one is the constraint, right?
So 7.
Obviously, because 2 will give us a bigger power, but 7 will be
Yeah.
lesser. You need
Oh,
7 to be present.
so then whatever 7 comes out to be is the answer. Okay.
Hmm.
So would the answer be 28? Because 180 by 7 is around 25, and then 180 by 49 is like 3. So 25 plus 3 is 28.
So basically, we have to look for the, if it's not a prime number, then you have to look for the primes that make it and see the power that comes, the least power that will come. 7 will give you the least power, 2 will give you higher power.
Yeah,
But it matters that 7 also has to be present. So the least power will come from 7, that will be the answer.
right.
In this case, it will be 28. Okay. Okay. Then there is also a theorem that we would like to at least understand. It says that the product of divisors of any integer n is n to the power d of n by 2, where d of n is the number of divisors of n. So d of n is the number of divisors of n, and we are saying that product of divisors of any integer n is this.
Yes.
So try to get a proof for it or why it is working.
Okay. So,
In general, take n as some P1, E1, P2, E2, let's say till Pk, Ek. Then
Right.
D of n is what?
D of n is E1 plus 1 times E2 plus 2 all the way to EK plus.
It's not
Oh,
E2
sorry,
plus
E2
2.
plus 1. E2 plus 1. And then all the way to EK plus 1.
Okay. Now, what we want to find out is product of the divisors. So, okay. So we have divisors would be like 1 P1, P1 square till P1 power E1. Then similarly P2, P2 square till P2 power E2.
Mm-hmm.
And also combinations of them, right?
Yeah.
Okay, it will be easier if you do a small number and see what comes. So let's look at 24 again. 2 cube into 3 power 1. The divisors are 1, 2, 3, 4, 6, 8, 12, 24.
Yeah.
When you're doing 1 into 2 into 3 into 4 into 6 into 8 into 12 into 24. Product of the divisors, we are getting 2 power 1 plus 2 plus 3, right?
Yeah.
And then there are some powers of 2 from here and here and here, right?
Yes.
There is 2 here, and then there is a 2 power here, 2 powers of 2 here, and then there are 3 powers of 2 here. Okay, so you can see that there will be another 1 plus 2 plus 3, right?
Right.
In the 6, 12, and 24, right?
Mm-hmm.
So normally the power should have been only 2 power 6, but it has become double of that.
Yeah.
Do you understand what I'm saying?
Yes.
If you just calculate what is the highest power of 2 that divides 24, you should have gotten 24, not 24. Like in these numbers, the total powers of 2, right? You are getting more powers of 2 because 6, 12, 24 also have 2 and 4 and 8.
Yeah.
And similarly for 3, you will get from here 1, and you get a 1, 3 from here, 6, and another 3 from here, and another 3 from here, right?
Yeah.
Okay, right. So we are getting 2 power 12 into 3 power 4. That is coming as the product of divisors. And actually, dn in this was 3 plus 1 into 1 plus 1, which was 4 into 2, 4 into 2, 8.
Yeah.
So, right. And n was 2 power 3 into 3 power 1. And this raised to the power 4 is giving us this, right?
Yes.
And 4 is dn by 2.
Yeah.
So it is working. However, we need to understand why it is working. So dn by 2 is being multiplied to n. Okay, so let's try to understand n power dn by 2. So n is p1 power e1, p2 power e2, pk power ek, whole raised to the power dn by 2, right? And dn is what? E1 plus 1, E2 plus 1 till ek plus 1
Hmm.
divided by 2. This is.
Yeah.
So we are getting, when you do this powers, you'll get P1, E1 times E1 plus 1, E2 plus 1, ek plus 1 divided by 2. And similarly, P2, E2 times same thing, E1 plus 1, E2 plus 1 till ek plus 1 divided by 2. And like this, right?
Yeah.
Why is this the product of the divisors of the number? That's what you have to think of. Uh, so we can say that P1 power, you can take the 2 here, and this is 1 plus 2 plus till E1 multiplied by E2 plus 1, E3 plus 1, ek plus 1. Okay, now I understand what is happening. See, what is this E1 into E1 by plus 1 by 2? Isn't that this?
Mm, isn't that just E1 squared plus E1 by 2?
How does that help us understand anything? I am saying what is E1 into E1 plus 1 by 2? Does that remind you of
Oh.
something?
Oh, it's like the natural number something. Yeah. The sum of the first n natural numbers.
Is the sum of the first E1 numbers.
Yeah.
If I take E1 into E1 plus 1 by 2 and think of it as this, the rest of the stuff is this, right?
Correct.
Why is this better? Because now we can think of it as P1. Now you're saying 1 times this stuff
Yes.
plus 2 times this stuff plus 3 times this stuff plus E1 times this stuff.
Right.
What is that? That is basically P1 1 times this stuff multiplied by P1 2 times this stuff, right?
Yes.
P1 3 times the same thing, this, and so
Yeah.
on till P1 even times the same thing.
Right.
These are all individual divisors.
Correct.
Why is this important? Because here we are getting different powers of P1, P1 power 1, P1 power 2, and the other divisors we have not done anything. We have left it the whole powers, all of the rest.
Right.
And you're getting P1 multiplied power 1 to it, P1 power 2, P1 power 3. These are separate divisors.
Yes.
Similarly, there are terms like this now, P2 E2 power this, right?
Yeah.
Then we will combine E2 and E2 plus 1 by 2 and think of it as the sum of first E2 numbers.
Right.
Do you understand what I'm saying?
Yeah.
And the rest of the divisors are untouched. Rest of the powers of E1 plus 1, E3 plus 1 till EK plus 1. And we can now split all of these in terms of the powers of E2,
Right.
which go up to powers of P2, which go up to E2. There will be one factor with P2 power 1 and the rest of the stuff is untouched.
Right.
Multiplied by another factor P2 power 2 and the rest of the stuff.
Yeah.
Do you understand what I'm saying?
Yes.
So what we are understanding now is how come n power dn by 2 became product of divisors. We wrote n, we wrote dn by 2, we wrote the expression for dn, then we multiplied the powers, we got something like this. Something like this is coming. Then we saw that here e1 into e1 plus 1 by 2 can be split as 1 plus 2 plus 3 till e1.
Right.
E2 into E2 plus 1 by 2 can be split as 1 plus 2 plus 3 till E2.
Yeah.
Because of that splitting, now we can separate the powers like this. We are using distributive multiplication, distributive law, and we are separating the powers. Once you separate the powers, you can see that it is actually a product of individual divisors where the powers of prime number P1 go from 1 to E1 and you get E1 different divisors, right?
Right.
Similarly, here you would get E2 different divisors, right?
Yes.
You're multiplying all of the divisors now slowly.
Right. Yeah.
Do you understand what I'm saying?
Yes, I understand.
The theorem is saying that product of all divisors is n to the power dn by 2, where dn is the number of divisors.
Yes.
If we take an example, let's say n is 12, number of divisors is what? 2 square into 3 power 1. So number of divisors is 2 plus 1, 1 plus 1, 6, right?
Right. Yeah.
Dn by 2 is 3. And let's find out 12 to the power dn by 2 we want to do. But let's understand how it will come. So 12 is 2 square into 3 power 1. And dn by 2 is, we will not write it as 3. That will defeat the purpose. We'll write it as 2 plus 1 into 1 plus 1. Or we can write it as 3 into 2. So this is dn by 2, right?
Right.
Now we'll separate it out and say 2 power 2 into 2 plus 1 into 1 plus 1 by 2, right? And 3
Yes.
power 1 into 2 plus 1 to 1 plus 1 by 2, correct?
Right.
We are not going to calculate it. Our point is to show that it's a product of the divisors of 12, right?
Yeah.
So we are going to rewrite it like this. Notice that 2 into 2 plus 1 by 2. That's like n into n plus 1 by 2, right?
Right.
So that is the same thing as 1 plus 2 till n. So 1 plus 2 only. Actually, if you calculate it, is obviously 1 plus 2. How much is this? This is 1 plus 2, right?
Yeah.
And here we have 1 plus 1 here.
Right.
Similarly, 3, here you have 1 and 1 plus 1 by 2, which is obviously 1 only. But what we are writing it as, we are grouping this term and these two terms together and thinking of it the sum of first one natural numbers, right?
Right.
Do you understand what I'm saying?
Yes.
And 2 plus 1 like this. And now we write it as this. So this is 2. You have 1 into 2 plus 2 into 2, right? And 3, you have 1 into 3. That's it here.
Right.
Correct?
Yeah.
So this can be written as 2 power 1 into 2 multiplied by 2 power 2 into 2
Mm-hmm.
and multiplied by 3 power 1 into 3, and I want to show that it is the product of the divisors of 12. So divisors of 12 are 1, 2, 3, 4, 6 and 12. So, right. So now this thing can be split as 2 power. See, you are getting 2 power 6 anyway. You would have
Right.
gotten powers of 6 as 1 from here, 2 from here, 1 from here, 2 from here. So 6 you would have gotten.
Yeah.
I just want to see how to write the divisors in a standard way. 1 second. 3 power 1 into 3. It is coming correctly. It's just that I wanted a nice way to split it out and write all the divisors. So 2 power 1 into 2, 2 power 2 is here. Still, the final split has not come clearly to me yet, but we already know why this works. It's just that it is difficult to show nicely the divisors. I thought we will get a nicer way to get it here, but right now, still we are not getting it in a nice way. But do you understand what the point is?
Yes, I understand.
Okay, we'll move on then. Question is, compute the sum of all positive integers whose positive divisors sum to 186. Sum of positive divisors is 186. All such integers, you have to find the sum of them. Are you understanding what has to be happening?
Yeah, we have to find the sum of the numbers. So I got that 186 is going to be like 186 is like 2 times 3 times like 31 because that's like the prime factorization. So then you get all the factors from it.
Sum of Actually, sum of the positive divisors of any number will be something like this: 1 plus p1 plus p1 square to p1 power e1 and so on. Is it possible for any of these type of things to be equal to 2?
No.
Because then p1 will have to be 1. P1 is a
Yeah,
prime number. It's not possible. So 2
right.
cannot be like a separate number here. You have to multiply it inside. So either you
Yeah,
will get a 6 into 31 or you'll get a 3 into 62, right?
yes.
Now you should check these cases. That 6, can we get 6 like this with a prime number? Can we get 31? Right?
Yeah. Um,
Because this is the actual sum of the divisors.
yes, correct.
You need to write 186 in such a way that 186 can be written in this way.
Yes.
You cannot group it as 2, 3, 31. 2 is not possible.
Mm-hmm. So 6, you could write it as like 1 plus 5, yeah, and then 31 would be like, could be like, would be powers of 2, like 1 plus 2 plus 4 plus 8 plus 16.
This is 15 and 16, 31. So that means if this is the situation, we are getting one way in which we can get 6 into 31, right?
Yes.
So what is the number then? The power of 5 is 1, right?
Yeah.
And here the power of 2 is 4, right?
Right.
So the number is 2 power 4 into 5, for which we can write some of the divisors like this: 1 plus 5 into this.
Right.
Do you understand what is happening?
Yes.
What is the other number?
Uh, so 3 is like obviously 1 plus 2. So 3 is gonna be 1 plus 2. And then 62. Um, I don't think anything adds up to 62 other than 1 and 61. Is that right? 1 and 61? Okay, yeah.
It's a prime number. 61 is a prime. So 1 plus 61 obviously will work.
Oh, yeah. So then the power of 2 is obviously 1. And then the power of 61 is 1 too. So,
122 is the other number.
yeah.
So basically, these are the two numbers which will have sum of powers adding up to 186. And you have to
Yes.
find the sum of all such numbers. So your answer will be 122 plus 80.
Right, so 202.
Okay. I'll give you some questions. We need to try them out before the next number theory class.
Okay.
First one is for some positive integer, for some positive integer n, the number 110 n cube has 110 positive divisors, including one and the number itself. Basically, normal, all the divisors, basically.
Right.
Uh, how many positive divisors? How many positive divisors does 81 n power 4 have? That's the first question. Then second one is the following number is the product of the divisors of the product of divisors of n. What is that number? 2 power 6 into 3 power 3. Find n. So that is a direct question based on our theorem, right?
Yeah.
We already know that theorem. We have to use that to get it. Then question 3 is how many positive integer divisors of 2004 to the power 2004 are divisible by exactly 2004 positive integers. How many positive integer divisors of this big number are themselves divisible by exactly 2004 positive integers? Okay, and last problem is n is equal to 2 power 31 and 3 power 19 product. How many positive divisors of n square? How many positive divisors of n square are less than n but do not divide n? The number is given. You have to find how many positive divisors of n square are less
Uh-huh.
than n but don't divide n.
Okay.
So write down these questions. These are the ones that we'll start off with in the next number theory class.
I wrote them down.
Okay, that's all for now then.
All right, thank you. Bye.
Bye.